Hi, welcome back. When we last stopped, I think we were talking about pure substances, which we said were elements and compounds. And we said we would talk a little bit about impure substances, which we call mixtures. So that's, I guess, where we'll start. What is a mixture? Well, a mixture is two or more substances mixed together, for lack of a better term. I know that's a horrible way to define a word, is to use the word when you're defining it, but it's the best I can do today. Imagine your bag of Lego blocks again. So let's say you're through playing with your Lego blocks. You're done with that, and so you put them all back in the bag. You tear everything apart, put them back in the bag, stick them back in your closet. Well, your Lego blocks are in close proximity to each other, but they're not snapped together. Well, that's kind of what a mixture is in a chemical sense. You have two or more substances, and they're in proximity to each other. They're close together, but they're not chemically bonded. All right. What that means is mixtures have different properties than compounds. In a compound, the compound has different properties from the elements from which they're made. In a mixture, each component maintains its own physical and chemical properties. All right. And so that gives mixtures a little bit different characteristics. In a compound, we talked about how they were always in fixed mass percents. I can have any mixture, any composition of a mixture. A little bit of this, a lot of that, half and half, so on and so forth. All right. Well, it turns out there's actually two different types of mixtures. You have what we call homogeneous mixtures, and you have what we call heterogeneous mixtures. Homo means same, so a homogeneous mixture is a mixture that has the same composition throughout. All right. Normally, what we call a homogeneous mixture, we call it a solution. Okay, so an example of that would be like sugar and water, like in a Coca-Cola or something, or coffee, say for example, would be a solution. Copper sulfate water solution. Those are called homogeneous mixtures or solutions. Why are they called that? Well, because I can take, say for example, a sugar water solution, and I can take 10 milliliter sample maybe from the top of the beaker, and I could take a 10 milliliter sample from the bottom of the beaker, and then I can evaporate off the water. And I can do this because, remember, in a mixture, each substance maintains its own chemical and physical properties. And so if I do that, what I will find is I'll find the exact same amount of sugar and the exact same amount of water in both of those samples, both of those 10 milliliter samples. It doesn't matter where I take it from in the beaker, whether top, bottom, middle, whatever. Every single sample in that beaker, if it's the same volume, will have exactly the same amount of sugar. And that's what we mean by homogeneous mixture. Okay? So when you think homogeneous mixture, just think solution. That's the easiest way to do it. If it's not a homogeneous mixture, it's a heterogeneous mixture. Hetero means different. So heterogeneous means different composition throughout. When I say the word mixture, probably what comes into your head is actually a heterogeneous mixture. So think of a mud puddle, for example. That would be a heterogeneous mixture. Something like Pepto-Bismol, for example, is what we call a suspension, but that's a heterogeneous mixture. Any kind of medication that you take that says like shake well before using, heterogeneous mixture. Okay, different composition throughout. All right. A good example of that may be like sand and BBs. Maybe I have a sand BB mixture. Okay, I've got the sand particles in there, got a lot of BBs. I could have a sand BB mixture with a whole lot of BBs and very little sand, or I could have a sand BB mixture with a whole lot of sand and very few BBs. It's still a sand BB mixture. There is no definite composition that you have to have like you do in a compound. All right. The nifty thing about mixtures is they're easier to separate than compounds. To separate a compound to its elements, you've actually got to do something. You got to do some chemistry, to get those atoms apart from each other. But since the substances aren't bonded together in a mixture, they're very easy to separate. So, say for example, I had my little sand BB mixture. How could I possibly separate those sand from those BBs? Well, one way I could do it very easily is I just stick a magnet down in there and kind of swirl it around. If I stick that magnet in there and swirl it around, the BBs will stick to the magnet because they're still magnetic, and the sand won't. And I can separate things out that way. That's one easy way to do it. Another way you may be thinking of separating our little sand BB mixture is I could pour it through a screen. The sand particles are really tiny, and so they'll fall through the little holes in the screen. The BBs are relatively large, so they'll get stuck on top. And that's a process called filtration. And we do this in a laboratory all the time with filter paper. Let's say I've got a liquid mixture, and it's got a solid in the bottom, and I want to trap the solid and get rid of the liquid. Well, the easiest way to do that is just to pour it through filter paper. Filter paper, if you looked at it under a microscope, is a bunch of little tiny fibers that are kind of running and laying on top of each other. And essentially what that is, it's like a little tiny screen. And so when you pour that through the filter paper, the water molecules are tiny enough that they make it in between the fibers and they go straight through. But your solid particles get stuck up on the top. And so if you pour it through the filter paper, your solid gets trapped on top, your liquid is down on the bottom, you've just separated out your mixture. So yeah, you'll use filtration in the lab quite a bit. Can I filter a solution of Dr. Pepper? Well, no, because the particles are really tiny and everything goes through. So what you get down at the bottom is you just get a lot of filtered Dr. Pepper, but it's still the same as the stuff that you poured through. So you can't do that with a homogeneous mixture. But yeah, with a heterogeneous mixture, you can separate it out very easily. What if I have two liquids? What if I have like ethanol and water, and I want to separate those out? Well, if I pour that through filter paper, it's just going to go straight through because they're both liquids. But I can still make use of the fact that they have different properties to separate them. And an easy way to do that would be something called distillation. Ethanol has a boiling point somewhere around 83 degrees Celsius, in that range. And of course, water boils at 100. And so what I can do is I can take that liquid mixture, I can heat it up past 83 degrees. The ethanol will boil, it'll change into a gas, it can go up a tube, and then I can condense it and trap it over here on the other side, through a little distillation column. And what I've got is essentially pure ethanol over here, and of course the water is still back over here in the pot because I haven't reached 100 degrees Celsius yet. Is it really quite that simple theoretically? No, not quite. Is it close enough for our intents and purposes today? Yes, it is. All right. And so, yeah, you're making use of the fact they have different boiling points, and that's how you separate it. Okay, and that's called distillation. Probably won't do that this semester. When you get to organic, you will do a lot of distillations, when you're separating out products. So yeah, these are two very common techniques that are used in the chemistry lab. And the reason they work is each particular substance maintains its own physical and chemical properties. And that's why you can do that. All right? Easy way to keep all this straight. If it's in the periodic table, it's an element. If you can think of a molecule of something, it's a compound. So carbon dioxide, that's a compound, CO2. NaCl, salt. If there's no such thing as a molecule of that, air, for example, paint, things like that, milk. If there's no such thing, as a milk molecule. If there's no such thing as a molecule of it, it's probably a mixture. And so if I gave you a substance, could you classify it as an element, compound, or mixture? If I gave you a mixture, could you classify it as homogeneous or heterogeneous? If it's a solution, it's homogeneous. If it's not a solution, it's heterogeneous. It's what you normally think of when you think of a mixture. When I say the word, a heterogeneous mixture is probably popping into your head right now, more than likely. All right? Okay. Well, that takes care of the matter part. So what else do we have to talk about here? Well, we said that changes. We talked about changes. When something changes, how do I know if it changes? Have I always been 6'6" since the beginning of time? Well, how would you be able to tell? What's the minimum number of observations that you can take to see if something has changed? Can you do it with just one observation? Well, no. I may have always been 6'6". Maybe I was born this way. It was a difficult birth. So what's the minimum number of observations you can make to see if something's changed? Well, that would, of course, be 2. You could have measured me back when I was 8 years old, and you could measure me now, and you can see that my height has changed. So therefore, you can conclude that Mr. Anderson wasn't always 6'6". There was a time when he was a little shorter than 6 feet. Sometimes it's useful to know if something has changed, but sometimes it's more useful to know how much something has changed. And so that's what we call quantitative change versus qualitative change. Qualitative change means something has changed. Yes, it has. Quantitative means how much. Well, if you're going to talk about how much something has changed, then what that means is you've got to be able to measure things. You've got to have a system of units. And so that's where we're headed next, measured quantities. What you're about to see, and I am not going to belabor the point because you've seen this before, probably back in school, and it is not the most exciting part of the course. I will grant you that. But it is in the chapter. It's in chapter 1, so yes, you are responsible for it. So I guess we probably need to cover it. What you're about to see is you're about to see something called the SI system. It stands for System International something. It's French. But basically, all the scientists of the world got together and said, you know what, we don't speak the same language, but if we could somehow speak the same mathematical language, well, you know, at least that's one thing that we've got going for us. And so we all got together and we all agreed on a set of units that we're going to use to measure things. What you're about to see is you're about to see a lot of metric stuff coming down the pike here. Why do we use metric units? Well, two very important reasons. One reason is it's just easier. You know, the metric system is based on powers of 10. And so if you have a prefix, which means something, and then you have your base unit. And if you know what the prefixes mean, and you know what the base unit means, then you know what the unit is. It's pretty simple. It doesn't work that way in the English system. You know, how many inches are in a foot? Well, there's 12. Okay, so there's 12 feet in a yard, right? Well, no, there's 3 feet in a yard. Oh, well, how many yards are in a mile? 3? 12? No. Many more. Okay? Just because you know something about inches, you don't necessarily know something about feet. And just because you know something about feet, you don't necessarily know anything about miles. How did you know there were 12 inches in a foot and 3 feet in a yard? Well, you memorized it. You were told that, and that was how you knew that. But there's no rhyme or reason. Probably is some reason why there are 12 inches in a foot and 3 feet in a yard. You just memorized it. When the metric system, everything is based on powers of 10. So you have these metric prefixes, which I'm sure there's a chart somewhere in that chapter that you can look at that. Just know the common ones. You don't have to know every metric prefix ever invented. Just know the common ones. And I'll let you look at that because you probably have already seen this before. And then you've got your base unit there. And everything's based on powers of 10, which also makes the math easier. You know, how do you divide by 10? Well, you just move your decimal place. You multiply by 10, divide by 10, multiply by 100. You just move in decimal places. Can you divide by 12 in your head very quickly? Can you multiply by 5,280? Well, no. And so the math is actually more cumbersome in the English system than it is in the metric system. So that's one reason why. The second, also very practical reason why we use the metric system in science is 98% of the world uses the metric system. Now, there's only 2 countries that don't use the metric system. Can you name one? Yeah, that would be us. That'd be the United States. The other is some island somewhere in the Caribbean, I think. That's it, though. Even the English don't use the English system. You know, the metric system is pretty much used around the world. So if you're going to use a set of units, you might as well use a set of units everyone is using, particularly if it's easier already. And so that's what you're going to see. You're going to see a lot of metric system units as we go through this. I'm going to try to blow through this fairly quickly because, again, not the most exciting part of the course. I think you have probably seen this throughout your high school and middle school education. So I'll let you kind of go at it. So what are some things that we can do? What are some things that we need to use to measure? We've got to have a toolkit here, right? Well, the first thing we measure is we measure length. Okay, what is the base unit for length in the metric system? Well, the base unit for length is something called the meter. Okay, sitting in a museum in France, there's this platinum iridium bar that has 2 marks on it. And that actually used to be what the meter was defined as, the distance between those 2 marks. And so people would come by and from countries and bring a bar and make 2 marks just as long as those 2, and then they had their own little standard meter stick. things get lost, things get broken, things get stolen, and so nowadays the meter is defined in physical constant terms. And so the meter is actually defined based on the speed of light in a vacuum. The speed of light is kind of the cosmic speed limit in a vacuum. Nothing goes faster than the speed of light in a vacuum. And it's equal to approximately 2.998 times 10 to the 8th meters per second. Well, basically what they did is they said, okay, well, a meter is the distance light travels in 1 over 2.998. It's a bigger number, more decimals, times 10 to the 8th of a second. And so what you've just done is you define the meter in terms of the speed of light. So if you have a very sophisticated timing device, you've got light all over the universe. That's not going to be hard to get. You can actually make your own meter stick, and you don't have to worry about physical things getting stolen or lost. Well, kilo means 1,000, one of the prefixes there. So a kilometer or a kilometer is equal to 1,000 meters. Now, quite often we put things in scientific notation. So how do I put this in scientific notation? Well, my decimal's right here. So I move my decimal 1, 2, 3, just to the right of the first non-zero digit, or the first non-zero digit here. And so that's 1 times 10 to the third. If you move it left, the exponent's positive. You move it right, it's negative. It's what the math people will tell you. The way I remember it, and I think it's easier, especially if you're slightly dyslexic. Long story, I'll tell you someday. Teaching did it to me. But what I do is if the number's greater than 1, it's positive. If the number's less than 1, it's negative. And I don't have to worry about left and right and moving and memorizing this, that. It's pretty easy. So use that if you want to or not. It's up to you. Centi means 1/100th, so a centimeter is 1/100th of a meter, which is 0.01. So if you move that decimal, you're going 2 places back here to the left to get to the 1, to the right. I told you, yeah. And so therefore that number is less than 1 times 10 to the minus 2, 1 times 10 to the minus second meters. All right. Milli means at 1/1000th. So a millimeter is a thousandth of a meter. If you have a meter stick and you see those little tiny lines on that meter stick, each one of the distance between those two lines is a thousandth of a meter. Okay, now if that's a thousandth of a meter, how many millimeters do I have to put together to make an entire meter stick? Well, I have to put 1,000 of them. So there's 1,000 millimeters in a meter. But each millimeter is 1/1000th of a meter. That's 0.001. Move your decimal 1 times 10 to the minus third of a meter. And then here's one maybe you haven't seen before, and it's nano. Nano means 1/1 billionth. Okay, so a nanometer is 1/1 billionth of a meter. If you had a nanometer stick, it would take 1 billion of them that you'd have to glue together to make an entire meter stick. A billion is, in scientific notation, 1 times 10 to the negative 9th. So a nanometer is 1 times 10 to the negative 9th of a meter. Now, why would I ever need something that tiny to measure things? Well, it turns out that when you're talking about dimensions of very tiny particles, so when you're talking about sizes of atoms, for example, usually measured in angstroms, but you could do it in nanometers. If you're talking about distances between particles, solute particles in solution, things like that, you're down on the nanometer scale. When you're talking about wavelengths of visible light, the light that's going through the room right now, that happens to be on a nanometer scale. And so this is a unit you're going to see pop up again somewhere down the road. So file that away for future reference. Nano, 1 times 10 to the negative 9th, or 1/1 billionth. Okay? All right, well, what about mass? What's the base unit for mass? And by the way, I get like 80% of you on a multiple choice test on this one. Most people will say the gram. It's actually not the gram, it's the kilogram, which is a kg. Of course, I can't get you on this one because you've already got filled out notes. That just makes the course not quite as fun. So kilogram, abbreviated kg there. Okay, why is it the kilogram? Well, sitting in a museum in France, there is a platinum iridium cylinder underneath a bell jar in a vacuum, underneath another bell jar in a vacuum, sitting in a vault in a safe, and that is the standard kilogram. A kilogram weighs about roughly 2.2 pounds. So a little bit heavy, but not much. Okay, kind of gives you an idea there. And that's the kilogram. And every other standard kilogram around the world is based off of that kilogram. Well, again, we talked about how having physical things is not really ideal because things get lost, stolen, corrode, whatever. And so what they did is they actually tried to redefine the kilogram, and they actually did last year finally decide. And it's basically based on a mass, what's called a force balance. Of course, force is equal to mass times acceleration in physics. Well, you can solve that for mass, just divide by acceleration, and so therefore mass is equal to force over acceleration. So if you take a certain mass and you apply a certain force to it, it will accelerate a certain amount. And so what they did is they actually defined it somewhat in terms of that. It's again a little more complicated, but that's the basic principle. So that they just use a physical law there, Newton's law of acceleration there to define the mass. They had thought about defining it in terms of a number of atoms of silicon, because we're getting really good at growing silicon crystals, as far as the computer industry goes. But they decided to go with the other way. So that's actually how it's defined. Now, why the kilogram and not the gram? Well, a kilogram is a relatively decent-sized object. A gram is a tiny mass unit. It's about the weight of a paper clip, roughly. You see, it'd be very hard to make something like a paper clip that accurate. So what they did is they made the kilogram. And so technically the base unit is the kilogram. Now, what if I wanted to define a gram? Well, I can say I need a mass that's exactly 1/1000th that of my standard kilogram, because 1 kilogram is equal to 1,000 grams, or 1 times 10 to the third. Should be grams there. I don't know why that says meters there. I guess I got to change my notes. All right, and that's how we define. We use grams in lab because you're not going to need kilograms worth of material, in lab. We can do it with a lot less stuff and pass the savings on to you, in tuition. So we'll see things in grams, but technically the base unit is the milligram, is the kilogram. Sometimes we deal with even smaller units, and one is a milligram. Milli means 1/1000th, so a milligram is 1/1000th of a gram, just like a millimeter is 1/1000th of a meter. See, if you know the prefix and you know the base unit, you're good. Makes it nice and easy. Okay? What else can I measure besides that? Well, how about temperature? Let's measure temperature. Okay? Well, it turns out there's 3 scales that you have to know temperature-wise. If I say it is 72 degrees outside, what temperature scale am I most likely talking about? Well, I hope I'm talking about Fahrenheit, right? Okay, because that's pretty comfortable. All right, the Fahrenheit scale, water freezes at 32 degrees Fahrenheit, and it boils at 212. Is that the temperature scale that most of the world uses? Well, no. The temperature scale that most of the world uses is actually the Celsius. And the Celsius scale is actually based on the freezing point and the boiling point of water. Water freezes at 0 degrees Celsius on the Celsius scale, and it boils at 100. Which one of these is actually the SI unit for temperature? Well, the answer is neither is the SI unit for temperature. The SI unit for temperature is something called the Kelvin, and this is also known as the absolute scale. And it turns out that 0 Kelvin, and notice that when you write temperatures in Kelvin, there's no degree. It's just 0 K. That's not a mistake. That's the way you write them. That's called absolute zero. And absolute zero is as cold as you can get. So, you look outside and you think, man, it's really cold today. I don't think it can get any colder. Well, it can. It actually can get colder. But there is actually a temperature where it doesn't get colder. How is it possible to get there? Well, when you measure temperature, you're not measuring heat content. That's something different. We'll talk about it later. When you measure temperature, you're actually measuring average molecular motion. You're measuring how fast the little particles are moving or vibrating. Okay? So if I want to lower the temperature of something, what I do is I slow that particle down. If I want to lower the temperature even more, I slow it down even more. Do you see I could keep slowing this particle down until I get to a point where the particle actually doesn't move at all? There's probably some internal vibration in there. Yeah, you probably by like Paul exclusion principle if you didn't. But yeah, you got a little bit of internal vibration in there, but the particle's not moving anymore. Okay. Do you see that I can't make that particle go any slower than stopped? That's pretty much it. Well, there you go. That's absolute zero. All right, and so that's 0 Kelvin. That's as cold as you can get. All right, well, there's my first point, but I need another point to figure out the size of the Celsius, Kelvin degree, right? Well, not really, because here's what we did. We said, okay, 0 Kelvin is as cold as you can get, so you're not going to have to worry about negative temperatures here, I suppose, in the Kelvin scale. And we're going to say every Kelvin degree is exactly the same size as a Celsius degree. So you've got a starting point, and you've got the size of each degree, and so you can make yourself a Kelvin thermometer. Make sense? And that's actually the SI unit. Kelvin, normally when we do temperatures, we do them in Fahrenheit here in America. In science, normally we measure things in Celsius. All right. However, there will come a time in the book where you have to put your temperatures in Kelvin. If you don't put your temperatures in Kelvin, you will get the problem wrong. Am I going to tell you when we get there? Yes, I'm going to tell you when we get there. All right? So, how do I convert between the scales here? Because I might want to change temperatures from Celsius to Kelvin or Fahrenheit to Kelvin or, Celsius to Fahrenheit. Well, here's a couple of equations that will kind of come in handy. Notice that when you agree with me, these are the same two temperatures, 32 degrees Fahrenheit and 0 degrees Celsius. And these are the same two temperatures, 212 and 100. This is the boiling point of water. This is the freezing point of water here. Okay? How many degrees do I have in between my Fahrenheit here? Well, 212 minus 32, that's 180. Okay, how about the Celsius? Well, 100 minus 0, that's 100. Okay, so you can see that a Fahrenheit degree can't be the same size as a Celsius degree because there's 180 degrees here and a Celsius and only 100 here. Since there's less divisions here, a Celsius degree is larger than a Fahrenheit degree. So how do I take that into account? Well, I'm going to take my degree Celsius over here and I'm going to multiply that by 1.8 or 180 over 100 or 9/5 back in high school. For some reason they like to use fractions in high school there. All right. And what that does is that makes these equal again. All right. But we've got another problem. At 0 degrees Celsius, I'm already at 32. So I've got a head start here and I have to account for that. So what we're going to do is we're going to add 32 over here to the Celsius side to make everything nice and even. And I come up with an equation that looks like this. Degrees Fahrenheit is equal to 1.8 times degrees Celsius plus 32. Something you probably have seen before. All right, you probably saw it with 9/5. They just love to make you do fractions in high school. Everybody just loves fractions, don't they? Just use 1.8. That's what I would do. All right. Now I could come up with another equation that would get me from Fahrenheit to Celsius. But if you think about it, if you're just can do any math at all, just halfway decent with algebra, you don't need another equation. Just plug in a number here, solve for that, or plug in this number here, solve for that. So that's only one equation you have to memorize, and that saves an extra space in your head up here for another equation or another piece of information that might become useful in tests. Now, if you want to, you can, subtract 32, divide by 1.8, and you get degrees Celsius equal to, Fahrenheit minus 32 divided by 1.8. You want to do that? Fine. It's easier for you to memorize two equations. But, I would just do it that way if it were me. To get from Celsius to Kelvin, it's easier because the degrees are the same size. So I don't have to worry about this factor over here. All I have to worry about is the fact that they start at different places. 0 Kelvin is negative 273, negative 273.15. You'll get real picky about it, degrees Celsius. So that is roughly negative 454 Fahrenheit. So will it ever get that cold outside? No, it won't. But, if it did, that would be as cold as it could get. That'd be pretty bad. But yeah, we don't get anywhere close to that out here. So to get from Celsius to Kelvin, all you have to do is add 273 or 273.15. When you get real picky about it, we'll probably add 273. We won't worry too much about that. But yeah, that's it. Okay. So problem time, for example, convert 72 degrees Fahrenheit to degrees Celsius into Kelvin. So 72 degrees Fahrenheit, room temperature, it's about what you're probably feeling right now. Nice and comfortable. Not too hot, not too cold. So to get to Celsius, I'm going to use that first equation. So 72 is equal to 1.8 times degrees Celsius plus 32. So we're going to subtract 32 from both sides to get that over here to the other side. So 72 minus 32 is 40. So 1.8 degrees Celsius, 1.8 times my degrees Celsius is equal to 40. Divide both sides by 1.8, and you get about 22 degrees Celsius. So when you see temperatures like 20 degrees Celsius, 25 degrees Celsius in your book, that's room temperature. When you see temperatures like 10 degrees Celsius, 0 degrees Celsius, that's cold. When you see temperatures like 35, 40, 50, 60 degrees Celsius, that's actually kind of hot. And so that kind of gives you an idea of what's hot and cold if you're not used to working with the Celsius scale. It gives you a break point there. So about 20 to 25 degrees Celsius is room temperature. That's a nice way to be able to tell. To get to Kelvin is pretty easy. You just take your Celsius and add 273. So 22 plus 273 is 295 Kelvin. Notice no degree sign. So if you see temperatures in the book like 295 Kelvin or 300 Kelvin, it sounds hot, but that's actually pretty comfortable. If you see temperatures like 250 Kelvin, that's cold. If you see temperatures like 400, 500 Kelvin, that's actually kind of hot. So that kind of gives you a feel for the scales if you're not used to working with it. That's room temperature. Make sense? Okay, one more unit, and then we will stop with the unit thing. I know it's kind of an exciting thing to talk about, but we'll move on. These are called derived units. Derived units are units that are, for lack of a better term, derived from your base units, which are defined. So, for example, volume. The base unit for volume is the cubic meter. Okay, now, why is it the cubic meter? Well, because I've already got my little meter stick, right? So what I can do is I can say, okay, well, let me make a box that's exactly 1 meter high and 1 meter wide and comes out 1 meter from the wall. And we're going to call that a cubic meter. And so you have defined the unit for volume based on the unit for length, which you've already defined. And that way you don't have to make a platinum iridium bowl that holds a liter or something like that. Now, a cubic meter, if you think about it, that's a lot of stuff. You're not going to really use that much in lab. So we use liters in lab. And actually, you probably use milliliters in lab. We use liters to mix things up. A liter is roughly 5% more than a quart. So it's about like a quart, something like that. A little bit more, about 5% more. And that's what we use in science, really. Sometimes you will see in British journals something called a cubic decimeter. A deci means 1/110th. It turns out that the way all this stuff is defined, a cubic decimeter is exactly the same as a liter. And so British journals use that because it's more in keeping with the actual SI unit. You know, that's British for you. Americans, we just use liters. Everybody uses liters. Okay, so we use liters, but technically, when we get real picky about things, the cubic meter is actually the base unit. And it's called a derived unit because it's derived from a fundamental unit that you've already measured or defined, which would be length. Okay, usually a liter is more than we use in lab, and so therefore you've got the milliliter. And milliliter means, of course, 1/1000th. So a milliliter is 1/1000th of a liter. And so therefore in a liter there are 1,000 milliliters. Okay. Now, sometimes you'll see a cubic centimeter, and that would be like a cm with a 3 there, or you'll see a cc. You see this in like hospitals and applications, things like that, maybe engine displacement or something like that. When you see a cubic centimeter, that's exactly the same as a milliliter. The way things are all defined, we won't get into it, they're exactly the same. So if you could express the density of a liquid in grams per milliliter, we'll say, but you could also express it in grams per cubic centimeter. It's the same number. It's the same thing. You could express the density of a solid in grams per cubic centimeter, but you could also express it in terms of grams per milliliter. It doesn't really matter. If it just bothers you, scratch out the cubic centimeter and write in milliliter, or scratch out the milliliter and write in cubic centimeter. They're exactly the same thing. Okay? All right. Well, that's units. And so now we have something that we can actually use to measure things when we go to lab. That's our toolkit. And there are other units, but we'll talk about them and we'll introduce them as they're needed as we go, because we're running up on a time crunch here. So that's a fairly decent place to start or to stop. But, before you go, I got a question for you, something to think about before you hit the next video. And that's this question right here. So a little pop quiz today. Okay, one question, you get 100 or 0. So I got 3 measurements down here. I've got 5 kilograms, I've got 5.0 kilograms, and I have 5.00 kilograms. All right, simple question. Okay, are those measurements the same or are they different? Same or different? Give it some thought. Watch the next video. Maybe we'll try to explain. All right, so have a good one. We will do our best to finish up the chapter in the next video. Bye for now.